Hello again. It's my privilege to welcome, Jensen Huang, who, of course, needs no introduction. Okay. And we had a partnership with Nvidia for a long time, and it's really remarkable to see, how Jensen and Nvidia is transforming the world. Okay. And also Jensen himself is running a master class for the last 30 years on how to lead a company, how to transform industries, how to create new markets. And it's really great to have Jensen here. Jensen, please.
Anirudh,
Yes.
it's great to be here. I love designers. I love design tools.
Yes.
I love Cadence.
Oh, thank you, guys. So,
I love them all. I love Virtuoso, Allegro,
Palladium?
Palladium. Palladium is the only appliance that's more important to me than the refrigerator. It is the single most important appliance in my life. We are the largest installation of Palladiums anywhere, you know that. And they are the first supercomputers we ever installed and operated. And we are incredibly enamored with Palladium. And so we love the work that you guys do. Blackwell would not be possible without Palladium.
Well, thank you, Jensen. We love this partnership. It's remarkable to see. And, you are now the godfather, right? Everybody just calls you the godfather,
Come on.
So, we can talk about a lot of things. But first, as the front row seat of driving.
When the godfather says something, it happens.
Yeah.
When the godfather wants something, it happens.
Yes.
Obviously, that's not true for me.
But in terms of AI, you have, of course, you have front row seat. You're driving most of this innovation. What do you see? Next 5 years, there's like models get bigger, models get more specific. What happens to the architecture of the data center? What do you see for next? Of course, this is a long-term journey, but especially for the next 5 years, how do you think AI is going to evolve?
I got that. Let's take a step back, and in fact, your keynote, Anirudh, is probably the most condensed example, highlight of the transformation of computing underneath. And the reason for that is, of course, as you know, without computing, without cadence, there's no computing. Without computing, there's no cadence. And so the fundamental transitions of the computing platforms underneath, it's foundational to cadence, and it's foundational to every single industry that relies on cadence, which is every single industry. And what's happening, if you look at your keynote, your keynote very clearly highlighted and in fact, Millennium alone highlighted the incredible benefits of accelerated computing. And once you get on accelerated computing, then the next thing that is possible, generative AI, is additive on top of that. Without that transition to accelerated computing, generative AI would be very difficult to do. The benefit of going to accelerated computing is all of a sudden, what was difficult to scale in the past using CPU scaling, all of a sudden, you're talking about 1,000 times X factors. And on top of that, another 30x X factor on top of that. When you add generative AI to that, there's another 100,000 X factor on top of that. You also said something that was really, really terrific in the beginning. You said that design tools does the processing one time. And yet what designers want to do is explore a multi-dimensional, multi-modality oftentimes, exploration space. And there isn't a right answer, there's simply a best answer. And so we need to explore hundreds of thousands of different areas. But of course, the universe, the exhaustive exploration of the design space is simply too hard to do. No,
Exactly.
An infinite amount of computation would not be able to do it. And so we need AI to help us jump into a particular area of exploration and optimization, and then using principled solvers, really home in on that. And so there's all kinds of different things that we can do together. So accelerated computing, I think generative AI, first of all, is going to transform the way that Cadence develops software, and it'll transform the way that we use software. I think that's number one. I think there are several other benefits aside from being able to do, well, we design our circuits, our chips, our PCBs, our systems, and now even our data centers in Cadence, right? You know this quite well. We use you for circuit design, to logic design, to system design, to emulation, to verification, formal verification, so on and so forth, end to end, all the way to fluids. And so the design space anymore is not about a chip or a system, but it's really a co-design that goes across the entire thing. Millennium is really quite an excellent example, because you're a co-design company by nature, we're a co-design company by nature. The way that the computer science industry, the computing industry talks about it, the way we talk about it in engineering is co-design, the way that's talked about in computing is called full stack. But it's the same idea, that you have to innovate across the whole thing. And so your transformation of Cadence from a chip design and EDA company to an EDA SDA company, I think is really visionary and is really essential. And that's kind of the way, it is in fact exactly the way that we work with Cadence and the way that we design systems. Now, some of the areas that people are starting to realize, and in fact your keynote is actually excellent. In fact, I recommend everybody watch it a few more times, because it's so dense. It is so dense. Now, of course, you and I speak the same language,
yes.
And so it's a
high bandwidth communication.
Yeah, exactly. You only had you said it once. You said it once, and I
Yeah.
you know, of course.
But you are unique in
it.
that. You are unique in that. You understand things like.
That's not true. I just understand you like. Both of us are engineers, and so and anyways, one of the areas that you touched on, which is really profound, is that by investing in accelerated computing, by investing in AI, by investing in data centers, we're able to design better and more energy efficient products.
Exactly. Yeah.
Now remember, you designed the chip once, but you ship it 1 trillion times. You built a data center once, but you save power, that 6% power that on MediaTek that you showed, that 6% is going to get enjoyed by 1 billion people all day long. So the amount of energy that we're going to be able to save for the world by designing better software, better chips, better systems has a perpetual benefit to society. And on the one hand, we're going to consume more power in data centers for AI. On the other hand, for the other 98% of the power that's consumed and energy that's consumed, we're going to reduce that. Design better products, design better computers, better cars, better phones, so on and so forth, better materials, so on and so forth. So I think we're at a really, people call it an inflection point, a transition. All of that is completely true, and I think really exciting times, and your keynote really highlights it.
No, thank you. One thing is remarkable. I mean, a lot of things remarkable about NVIDIA, but one thing is truly remarkable. This transformation, and you talk about it and you probably always had it in your mind of transforming, not just making chips, because people confuse NVIDIA. Of course, NVIDIA is making the best chips, but even your keynote at GTC, is building entire data center, entire systems, entire software stack, and putting them together. You have racks and liquid cooling data centers. So the whole architecture, that's not easy transformation for a typical chip company. And now NVIDIA has become like a whole software system company, right? So I'm just curious to see, how did you do that, or you always had this in mind, or how did it unroll from? This is very difficult to implement. Now, some companies system companies are trying to do chips, which is difficult. But NVIDIA has executed this flawlessly, this transformation from not just chips to systems to software to data and all that. So I'm just curious how you go about something like this. Yeah.
Well, I think the most important thing you said just now was flawlessly.
Yeah.
You know, this entire audience, all of us grew up together.
Yeah.
And I've been a chip designer for a very long time. This is my entire career. And so there are many people in the audience who, when you said flawlessly, I'm sure the audience went, really? There are several things that we observed a long time ago, which turned out to have been right. Okay, and so the first thing is to observe that a small amount of the code in a program represents the vast majority of its runtime. So, for example, CFD, it's probably, call it 3% of the code represents 99.9999% of the runtime. And if that's the case, why do you use exactly the same tool, the same instrument, the same processor to process all 100% of the code? Why don't you do something for 97% of the code and then something special for 3% of the code? And by doing so, you could speed up an application 100,000 times.
Yes.
That was the observation. And of course, the type of applications that require that benefit from that would want to do the rewrite was very, very small. And we were clever to have chosen computer graphics as our first choice for accelerated computing, because it turned out to have been an application that required a tremendous amount of computation in a parallel way. It's conducive to parallel processing, and it's also a very large market that churned very quickly, that innovated very quickly. And so we chose a good market as a starting point, but we always imagined that beyond computer graphics, there would be a whole bunch of other applications that would come along. Accelerated computing is not like general purpose computing. In general purpose computing, you could create one processor and it will run all code. That is absolutely not the case with accelerated computing, because in fact, I coined the word accelerated computing, and what I meant by that was you accelerate an application. It's an application acceleration computing platform. And you have to know what application is.
Yes.
And so in the case of NVIDIA, we started by selecting computer graphics, but we also did imaging, and then we did molecular dynamics. I'm so happy to see the work that you guys do in digital biology. By the way, just as a quick, today we call it drug discovery.
Yes.
The reason why we call it drug discovery is because it's a little bit like, mushroom discovery. You go out into the forest and then you go, oh, look what I found. Could you imagine if the chip design industry was called chip discovery industry? and the reason for that is because my engineering team would come out, hey, Chancellor, look what we found. Blackwell. And then next year it would be like dry spell again.
Yeah.
Nothing happened. What happened this year? We didn't find anything. Completely understandable, But we would never do that, isn't that right? And so that and the reason for that is because biology is much, much more complicated. We shape a transistor until we could use design tools on it. You can't shape biology until you could use design tools on it. You need design tools to catch up to the biology,
exactly.
which is near. And so I think one of the largest industries in the world is going to become a cadence industry. And instead of that 1% you were talking about, I think there's a giant opportunity ahead. Each one of the industries, biology, you mentioned transportation, all of the applications are different. And some of it's related to imaging, some of it is related to particle physics, some of it's related to fluids, some of it's related to finite element, grids and things like that. And so the algorithms are different. And the fact that Cadence is a mathematics and a computing company, in a lot of ways, NVIDIA is a mathematics and a computing company.
Yes, exactly, yeah.
And that's the reason why we get along so well.
Absolutely.
Yeah, and when Anirudh and I get together, we're saying things to each other, and very quickly we understand. When I understand something, I nod. When he understands something, he shakes his head like that. And so, is it me? It's not, right? It's not me. I know for a fact. And so when you see the two of us, we're at a restaurant and we're talking to each other about all this stuff in the future. One of us going like this, and the other one's going like this. And that's because we're agreeing with each other. as soon as I go like this and he goes like this, that means we're in trouble. And so anyways, we were always about domain-specific acceleration. And over the course of 30 years, we've accumulated on top of one architecture we call CUDA, all of these different DSLs, domain-specific libraries. And some of it's for particles, some of it's for imaging, some of it's for artificial intelligence, and so on and so forth. Yeah.
And then, you know, this platform, of course, and you had a great talk at GTC. That's remarkable. That's why I was telling Jensen, he needs a bigger stadium next time, you know. That there was no enough space in that huge stadium, so maybe next time you find Vegas or I don't know where you're going to be. But there are so many applications you highlighted, you know. I mean, there's horizontal enablement of almost all industries. Yeah. But then there's certain industries, the impact can be huge, like you mentioned life sciences, but you also talked about robotics, you know, or self-driving. Yeah. So is there one or two that, of course you're involved in so many, that you're super excited about in the short term or medium term that has the maximum potential of impact?
Well, you mentioned several of them. The three industries that you highlighted happen to be the three industries I'm super excited about as well. One of them is data centers, or just computing. The second is you mentioned automotive, but if I could just abstract automotive into robotics, autonomous machines, autonomous systems, and or semi-autonomous systems. That whole general category, whether it's cars or trucks or pizza delivery robots or humanoid articulation, self-articulated robots, those kind of systems have a lot of commonality. They all need to have multiple sensors. They require, the functional safety is really important, so the way you design the computer and validate the computer, verify the computer, certify the computer, very, very important. The operating system is not your normal type of operating system. These operating systems are fail-safe operating systems, and so the way you design the system is quite meticulous and quite specific, and of course the use of artificial intelligence quite expansive. And those systems will be connected to the cloud, to the data center at all times, so that it could of course update new experiences, report failures and new circumstances, and then download new models. And so that I love that entire area of autonomous systems. A whole new category of devices for all of us to be building in the near future are going to be humanoid robots. And you could just see that the manufacturing cost of a humanoid robot is likely to be a lot lower than people would expect. Why would it be any more than $10,000 to $20,000? And you buy cars for $10,000 to $20,000. Why can't you have a humanoid robot for $10,000 to $20,000? And that robot will likely be a lot more agile and more versatile in an environment, in a world that we designed for humans. And so manufacturing lines were designed for humans, warehouses were designed for humans, a whole bunch of things were designed for humans, and therefore it's more likely that a human robot would be productive in that environment. So I love that. I love that we're going to turn biology into a field for engineering. The scientific discovery process really essential, but it's sporadic, and it's the reason why the E-room, the E-room law is true.
Yes.
And by the way, if we don't move to our accelerated computing, if we don't go to AI, the computer industry will go through the E-room law. And the reason for that is very, very clear. The amount of work that we do, the computation that we do is growing all the time, but CPU scaling has slowed, and therefore we're going to enjoy inflation and not reduction in cost of computing. And so we have to move to accelerated computing to save power, save time, save money, but anyways, I think digital biology is going to go through a whole renaissance where science and engineering comes closer and closer. It's a very complicated field, obviously. We don't talk about Schrodinger's equations in chip design because we changed the transistors until we could avoid Schrodinger's equations. But unfortunately, in biology, covalent bonds, the way that chemistry works, obviously Schrodinger's equation is essential. And so I think there's a whole lot of things that we have to go innovate. But for the very first time, we have the necessary tools, the computing systems, the algorithms that helps us deal with very large systems that are very chaotic.
absolutely.
Yeah, and the data-driven approach fused with what you said earlier, principled simulation approaches, that fusion might give us a chance. Yeah. But those three industries, I think, are spot on.
Yeah, these are huge. All
Yeah,
of them.
yeah. Enough.
But robotics.
Planetary scale is enough.
Yeah. Because automotive anyway is going to be like, with self-driving maybe the first robotics, but then humanoid is another huge.
That's right, exactly.
And then, I would like you to, of course we have this great partnership I really value, and like started on the chip part, system part, Palladium part, but now recently in bio, and then also in reality, right, in data centers, right?
Yeah.
So the one big issue there is, of course, power.
We use Cadence to design our data centers.
Yeah, thank you. So the issue of power.
Because a computer is a whole data center now.
Right, exactly.
Yeah.
But what's your thought on like power that AI is taking, the data centers are taking? Of course, we can optimize it, but what else can we do for this? One way to do it is if you do more accelerated computing, actually, what people don't realize is that your power utilized is going down for
That's right, yeah.
But just your thoughts on power consumption of AI and what all can we do in that?
Yeah, there's two things. So first thing that you said, absolutely true. The power usage of accelerated computing is incredibly high. And the reason for that is because the computers are incredibly dense. And so the power consumption is high, and whatever optimization we can do for power utilization translates directly to more performance. And that performance could be measured as in more productivity, generating more revenues, or directly into savings. For the same amount of performance, you could buy something a lot smaller. Okay, and so I think power management in accelerated computing directly translates into all the things that you care about. I just said something that seems right on observation, but in fact, the second thing you said would suggest that it's in fact completely wrong. And what we mean by that, and what Anirudh was implying, is that accelerated computing, as you saw in his presentation, took tens of thousands of general purpose servers, which would have consumed 10 times, 20 times more cost, 20, 30 times more energy, and reduced it into something that is incredibly dense. And so the density of accelerated computing is the reason why people think it's power hungry and costs a lot of money. But if you look at it from ISO work done or ISO throughput, in fact, you save an enormous amount of money. And that's the reason why it is essential, as CPU scaling has slowed, that we have to move towards accelerated computing, because you're not going to be able to keep scaling out that traditional way anyways. Right. And so accelerated computing is essential. The second thing that you highlighted in your keynote, you just have to pay super close attention. You were so crisp on it, that AI actually helps people save energy. If not for the AI models you created that we now use in the tools, how would we have found 6% more savings or 10x more savings? That wasn't possible without AI. And so you invest in the training of the model once, and then millions of engineers like ourselves get to benefit from it, and billions of people across decades will get to enjoy the savings. And so that's kind of the way to think about cost, the way to think about investments, not just on an instance-by-instance basis, but in healthcare speak, longitudinally. You have to look at savings, look at climate change, look at money savings, energy savings, longitudinally across the entire span of not just the products that you're building, but the way that you're designing the products that you build, and the impact of the product being used. When you look at it longitudinally like that, AI is going to be utterly transformative in helping us with climate change, using less power, be more energy efficient, so on and so forth. And
the great thing is that, with this 3-layer cake that I talk, there's a massive alignment in terms of between Nvidia and Cadence. You are transforming. Now, by the way, Jensen is a
Why am I always on the bottom of the cake?
No, you are in all 3 layers, Jensen.
Just kidding.
Yeah,
I'm just kidding.
All 3 layers. Yeah.
I want to be the frosting.
Yeah. By the people on Jensen is also, you had like homemade cookies last time I met you at Nvidia.
I'm a great host.
Yeah.
Anybody would drop by, I'm a great host. I always take care of them.
Yeah, thank you. No, it's great to partner with all these 3. But one thing, Jensen, you also have a very unique management style, right? Your leadership style is well known, flat organization, fast decision making is truly remarkable to see. And there are a lot of people, engineers and managers and leaders in the audience. So any advice you have for those things, how to turn, because turn ideas into action,
At the core of NVIDIA's management system and leadership philosophy, if you will, is to create the conditions by which amazing people could do their life's work. That is it. And I just described a philosophy, a mission statement, if you will, and a way of conduct of myself and the leaders. And so the question is, what can we do to create the conditions by which people could do their life's work? One of the most important aspects is to empower them with information. And so I don't think there's any decisions I make where only one person needs to hear it, or that I need to whisper some information to somebody on a one-on-one because nobody else deserves to hear it or can hear it, or too tough to hear, or whatever it is. And so I tend to do most of my work in large environments where a diverse team of experts and people who can contribute comes together, and we just work the problem, we just work the issue. So that's one. I also like that in addition to the transparency of the challenges of the company and the information that people should get, I also like that I have an opportunity to reason through things in front of people. It forces us to make suggestions of directions that are fundamentally grounded on good reasoning. And so by forcing myself to reason through things, I'm doing two things. I'm of course influencing others. Second, teaching other people how to reason. And the ability to take a very complicated abstract idea and reason it all the way down to exactly what we ought to do now, why we should do it now or not do it now. Most of the time is about not doing it now, or not doing it at all. That reasoning process is incredibly empowering to people. And so I think it's one of the reasons why NVIDIA is so small. We're only 28,000 people large, but we punch so far above our weight because almost everybody is empowered to make good, reasoned, first principled reasoned decisions on my behalf. And so that's kind of the reason why we did what we did. And then finally, the properties of your organization should reflect the product that you make. And NVIDIA is a full stack company. We're just like you, we're completely co-designed. And co-design suggests right up front that you shouldn't be doing something just with a hardware team. You shouldn't be doing something just with the software team. You should be doing something across everything at the same time because you're doing co-design.
Yes.
And so I try to create an environment where the experts and the contributors at every single layer of the company can be engaged with a problem, engage a problem at the same time. And so those are some of the principles.
Yeah, it's remarkable. It's remarkable to see.
Well, it's remarkable what you guys have done.
Yeah, no, thank you. It's a great partnership, Jensen. We are out of time, but thank you for the partnership. It's great to work with NVIDIA. Great to be a part of this massive transformation you're leading for the entire world. So
thank you very much, and thank you for your partnership.
Yes, thank you.